be compared to population 2. Okay, the proportion of population 1 to population 2. And we want to see, is there evidence to say that they're different? Now we know that difference means that they're not equal to each other, which means that the null position must be that the proportion associated with population 1 is equal to the proportion associated with population 2. And we assume the null to be true. Okay? Now, a consequence of this particular statement here, okay, a consequence, okay, of the assumption, okay, that H0 is true. The important thing of the assumption that H0 is true is that we have pi 1 equals pi 2, okay, and therefore we must have pi 1 minus pi 2 must be equal to 0. Okay, so actually now we know what pi 1 minus pi 2 is. Under the null hypothesis, it's actually being hypothesized that the difference is equal to 0. In other words, there's no difference between the proportion associated with the population of sample 1 compared to the proportion associated with the population of sample 2. In other words, there's evidence, the null position is that they've been selected from the same population. Okay, if that makes sense, because their proportions are the same. The difference is 0. Okay, so now we have everything with respect to our test statistic. This pi 1 minus pi 2 is effectively 0. So we know that step 2 in a hypothesis test, okay, that step 2 in our hypothesis test is going to be where we define our significance level. So step 2 is our significance level, okay, level. And in our case here, we have to undertake this at the 5% level of significance. We identified that earlier on when we identified all of our values. So we have alpha must be equal to 0.05. Okay. Step 3 is to calculate this test statistic. So step 3 is our test statistic. Okay. Now, our test statistic is z, okay, is equal to p1 minus p2. Now just keep in mind here that depending on which sample we call sample 1 and sample 2, this can be a different value. But just to keep in mind which one we put in. So sample 1 is going in as P1, okay? So that's 0.9, so it's going to be equal to 0.9 minus sample 2 is P2, okay? The proportion associated with sample 2, which is 0.8, okay? Okay, that's the first bit, minus, what is pi 1 minus pi 2? Well, under the null hypothesis, under the null, which we assume to be true, okay, pi 1 minus pi 2 is equal to 0. The proportion that we'd expect in population 1 minus the proportion we'd expect in population 2, the difference between them is 0, as in there's no difference, okay? And that needs to be divided by, okay, the square root of p bar. Now we already calculated p bar to be the sum of the totality of the successes across both samples relative to the total pool sample size, okay? And we got that as 0.84. Okay? So what we now have is this, is we have p bar is 0.84. That needs to be multiplied by 1 minus 0.84, which needs to be multiplied by 1 over the first sample size, which is n1, which is 108. Okay, 120, okay, plus 1 over the second sample size, which is 150, okay, and it's the square root of that, and it's the square root of this particular value, okay. So if we do this in stages, we end up with that the z-score that is effectively the difference, the distance between the two pieces of evidence relative to the null hypothesis, okay. Well, the numerator is going to be 0.9 minus 0.8 gives us 0.1, okay? Minus 0 is still 0.1. And the denominator, this particular square root, okay, we're going to do it in stages, okay? I'm just going to do this fractional amount here first. 0.84 multiplied by 1 minus 0.84, okay? So it's 0.84 multiplied by 1 minus 0.84, okay? Probability of success multiplied by the probability of failure effectively here, okay, and that gives us a value of 0.133. So these two factors here multiplied together gives us 0.1344, okay. So we have 0.1344 is this number here. And now let's do this particular summation here. So it's 1 divided by 120, okay. Oh, it's 1 divided by 120, okay, plus the fractional amount of 1 divided by 150. okay, which gives us a fractional amount of 0.015. So this amount here is 0.015, and it's the square root. When we get this done, it's the square root of this quantity here. So what do we end up with? We end up with z is equal to 0.1 divided by, and let me do this bit here, it's the square root of 0.1344 multiplied by 0.015, gives us a value of 0.0, let's just go to 3 decimal places, 045, which gives us a value of 0.1 divided by 0.045, gives us a value of approximately, it's 2.2, so approximately 2.22, okay? So that's our test statistic. Okay. So now what we need to do is we need to calculate our critical values. Is this, we're 2.22 standard units away from where we think the difference between the two distributions should be. Okay, 2.22 standard units. Is that far enough away? Well, let's see. So that's where our critical values come in. So step 4 is to calculate our critical values. And don't forget, this is a z-statistic, so it's going to be a z-curve that we're dealing with. So it's going to be a z-curve. Okay. The important thing also is that there's no directionality. I'm not hypothesizing. I'm not trying to test whether the proportion of sample with respect to population 1 is less than population 2, or whether the proportion of sample 1, population 1 is greater than population 2. I'm not trying to test that. I don't mind whether it's greater than or whether it's less than. I'm just interested in whether it's different. So actually, this is a 2-sample test. So this is not a 2-sample test, this is a 2-tailed test. So we're going to have to take our significance level, and we're going to have to split it up, okay, our significance level, and we're going to have to throw it in to both tails.